Welcome to HAO Colloquium. Our today's speaker is Daniela Lakatos. Daniela Lakatos received her PhD in 2019 from Monash University, Australia. She then joined HAO NCAR as an Advanced Study Program Fellow. Her work focuses on understanding a variety of quiescent and flaring chromospheric phenomena using spectroscopy, data analysis, and atomic physics. Daniela is also interested in how the solar chromospheric emission relates to the overlying coronal and underlying photospheric structures. Today she will be speaking on emission characteristics and evolution of solar filaments. To Daniela.
Thank you very much. Thank you for everyone for coming. So as Masumi said, today I'll be talking about filaments and their emission characteristics and how they evolved. I'll be using a variety of data sources. So first I will be discussing filaments using modern observation from IRIS, but I will also be looking at TOS past data from the Skylab era for more extended characterization of the emission in a wider range of wavelengths in the near ultraviolet. But first, a little bit about filaments and prominences. Filaments are very dense structures of chromospheric material that are suspended at coronal heights by the magnetic field. They're generally formed along polarity inversion lines, where there's the filament structure forms, and the shear field can support the material of the prominence of filament. When seen on disk, it's seen as a dark filamentary structure, but when seen at the limb, against the black background of space, the filaments are called prominences and are seen in emission. And depending on their lifetime, on their position on disk in relation to other structures, they can have a variety of lifetimes. For instance, filaments that are located close to the edge of coronal holes can live for a few solar rotations, even if the filament's channel is present for a couple of solar rotations, if the filament itself varies or can be seen only over parts of the polarity inversion line. In active regions, filaments have a much more complex and fast lifetime. They quickly evolve as twisted magnetic field, but because the magnetic environment in which they are present is very complex, they can quickly reconnect and get erupted. An eruption is also possible for the more stable long-lived filaments, but for those, it's generally they can become destabilized by either other events that happen close by, or by simply they get destabilized by flows within the filament itself. In this talk, I will be mostly talking about the emission seen in the near ultraviolet. And from this region of the near ultraviolet, I'll be mostly focusing in the first part on the magnesium to resonance lines at 800 nanometer angstroms. But I also, in the later part of the talk, I will be discussing about the emission of prominences on a larger wavelength interval in the near ultraviolet. I'm interested in the magnesium 2 lines because these have contribution to their formation in various layers of the solar chromosphere. For instance, you have parts that are formed just above the temperature minimum at the top of the photosphere. The bulk of the contribution comes from the temperature plateau in the chromosphere, while the center of the line is formed very high up in the atmosphere at the bottom of the transition region. Because the magnesium has such a wide range of the emission of magnesium comes from such a wide range of chromospheric heights, looking at different locations within the profile can give information about the height structure within the observed solar feature. if we look at the detailed profile of the magnesium, its height is very complex. Here I'm showing the resonance lines, so the magnesium K and H, that correspond to transition from the first excited state of the singly ionized magnesium ion to the ground state. In blue, you have the magnesium K line, and in red, the magnesium H line. Both these lines have complex inner structure. They are found in very deep absorption rings, and at the location where the line goes into emission, we have the so-called outer minima. Then we have two emission peaks to the blue and to the red, and in the line center we have an absorption core. This complex structure is also given by the very high optical thickness of this line, and the different features of the profile will be therefore observing very shallow layers within the atmosphere. So this is a typical profile, but if we scan over wider observation, we see that the individual characteristics of within the profiles have a very wide range of shapes and properties. The two emission peaks within a single line can dominate or can change up there which one dominates over a particular structure. The depth of the center reversal can also change quite a bit, and also the width of the profile and relative position will also change depending on if the plasma that is emitting this emission is moving or it's stationary. As I said before, if we look at the different position within the line, you can see different structure going into the line. You can see higher in the atmosphere, and towards the center of the line, you can see a very tubular structure that corresponds to the top of the chromosphere. While at the towards the outside of the line, we only sample the very high photospheric top of the granular structure. So in this study, I will be, as I said, mostly using IRIS data. IRIS is a slit spectrograph that is capable of scanning various scanning with multiple steps at given structure. In the top left image, we have example of such a scan. So of the structure, we have multiple position of the slit. For each of these, we have a spectra like the one on the right. But we need to bear in mind that especially if we are dealing with the scans that has a lot of steps, the structure itself will vary while the scan is happening. So, for instance, in scans like this for almost 400 steps, it takes about half an hour to complete a scan. So the structure itself will be evolving that the scan is happening. So the structure within the same map, the structure at the beginning is not the same as the one all the way at the end of the scan. In this study, I will be showing two filament observations. Because one of them is shown here. At the top, I show the SDOIA 304 and 193 for context. The filament is located in the middle of the panel here, and the dark border shows the location where IRIS is pointing. And for each of this position, we have spectroscopic data for the region. I'm also showing here multiple dots of different color dots. These are to show the variability of profiles within the field of view. For the filament, the continuous lines are in general characterized by a very relatively high peak separation, but all of them have very deep absorption, center absorptions of the magnesium K line. When compared to the quiet sun, which are the dashed lines, but these are quite unexciting when compared to the more active points that are shown in the dotted line, where the center reversal is almost filled in, and we have very high asymmetries of the lines. A very similar, another data set that's very similar. I'm showing the same thing, AIA at the top, magnesium integrated intensity on the lower left, and some sample profiles. Again, we have a very deep absorption in pixel overlying the filament, high peak separation when compared to more quiet sun, and well, in active pixels, we have very high intensities and very asymmetric profiles. In order to explore the different characteristics of the profiles, we can start by doing a simple profile analysis while looking at the integrated intensity, so simply integrating, summing up all the intensity under the emission profile, or then we can look at the shifts of the line centroid, so motion of the whole line profile from reference position, which gives a little bit of shift, and we can also see variation of optical line width, which corresponds to non-resolved motion or turbulence within the observed structure. We can also look at the details of the profile, and this will give us much more information about the formation height of those particular features within the profile. For this, I have a very simple algorithm that identifies the different profile feature based on a quartile analysis. I'm identifying the minimum position, the center revolve, so I identify a minimum position close to the 50% percentile, and then I'm looking for peaks to the left, to the blue, and to the red. For the outer minima, I'm using the red word outer minima because the position close to the position of the outer minima towards the blue, there's also an iron line that will be identified as the minima, that's just not the true minima of the profile. After I have identified these features of the profile, we can look at the relation between these identifier features. The simplest one is the separation of the peaks, so how far apart the red and the blue peaks are regarding one from another. We can then look at which of the peaks, the emission peaks, dominates the emission, which will give us an indication of the line asymmetry, and then we can investigate how deep the absorption feature is relative to the surrounding emission peaks, which will give us the depth of the center reversal. If a similar feature identification is run on the H line, so the other resonance line, we can take ratios between the features, the intensity of the different features, and this will give us an indication of variation of optical depth within the structure we are analyzing. So now let's see how the filament looks like in these various observables. In the integrated intensity, this filament, for instance, has a very important, very unusually deep center reversals. So the contributions from the peaks are also washed out a little bit, and the filament is also visible in the integrated intensity, but this is not usually the case. In most integrated intensity maps of filaments, this will be dominated by the emission peaks, and the filament will be almost never visible. But the most easy way to see the filament is look at the center reversal, the position of the center reversal and its intensity. This because the center reversal is for the highest in the atmosphere. We see the top of the emitting filament, and you can see the different, also beside the bulk structure of the filament, you can also identify different filamentary structures, substructures within it. And this is useful because if you need to choose, if you need them to look at behavior or variation within the filament material, we can make a very straightforward delimitation based on how we can easily identify the filament based on its intensity at the position of the central reversal. You can also look at the intensities at the emission peak. So here on the left, I'm showing the intensity at the red emission peak. And here we can also barely see some indication of the filament, but only a little bit. But if you go further out towards the wings at the outer minima, this is, as I said, dominated by the emission from the top of the photosphere, and the filament is no longer visible. So the filament is definitely only seen in the features of the magnesium that are formed higher up in the atmosphere, close to the top of the chromosphere. Another interesting characteristic is interesting characteristics that are kind of related to each other is the line width and the peak separation. So we can have on the left we have the line width, which is corresponding to unresolved motion that are broadening the profile, while the peak separation, while they do correspond to also sensitive to unresolved motion, these are more indicative they are more indicative of positions where you can also, for instance, you can have profiles that have very large peak separation, but have very narrow profiles, while you can also have profiles that have low peak separation, but the profiles are broadened by the non-thermal motions and have a very wide profile. In the peak separation, we can still identify some of the filament structures, especially towards the middle here, where the emission is a little bit more stronger. This is the most interesting result from this filament. So here on the left, I'm showing the line shift, so the Doppler shift of the line, and on the left, I'm showing the asymmetry, proxy of the symmetry of the line, so which of the peaks dominates the emission corresponding to each other. During the scan of this filament, we have flows that have a very high component along the blue earth component along the line of sight that has happened. That is the flows that are going on towards at the bottom of the filament, while in the filament itself we have a very stronger redshifted component. So at the bottom of the filament we have material that is flowing towards the observer, while in the filament itself we have flows that are flowing away from the observer. But bear in mind that this is only seeing the line of sight component of the flow, so most of the flow that when seen in imaging observation, most of the flow is happening along the filament structure. So we have flows that are carrying material within the filament that have various components, line of sight components that are dominating depending on where in the filament you are. And the same is shown by the peak ratio, so which of the peaks dominates. For instance, in the regions that correspond to blue shift, we have the red peak dominating, while flows within the formation height of the blue peak will spread out the red peak and reduce its contribution to the overall measurement of the Doppler shift. And the same is true same is happening in the filament where the blue peak dominates while the red peak is more spread out. And the final set of measurements are the measurements of the relative depth of the central reversal. On the left, here we can looking at the depth of the central reversal, we can see individual strands within the filament that have very similar similar profiles in regards to their optical depth. There's optical depth at the central reversal, and therefore you can identify using how deep the central reversal. You can identify the different strands within the filament. And when looking at the ratio between the intensity at the central reversal for the K line and the H line, this is proxy for the variation in optical depth within the filament structure. So here we have a very dark region which corresponds to the spine of the filament. This corresponds to the spine of the filament that has a very high, very low ratio between these two. This indicates that the material is very far from the optical thin condition that will make the ratio between these two lines 2:1. So it's almost 1.1 or almost 1. So the different within the filament, we can use these different observations to identify the strands based on both how optically thick the different strands are, or how the central reversal is highlighting the different flow structures. Because this was an interesting filament and had a very interesting flow happening along the lower part of the spine, I also looked at the observation that sit and stare observation that's located as the blue line shows. And I will be showing how the variation of the different parameters over a region that also only overlaying the filament here, as shown by the red bar. So over a period of a few hours, we are looking at the variation of the filament along that one position. This will give us information about that one position, so it will not be given, but we'll be missing the how the total changes, what total changes are happening within the filament. It's the larger filament. So within this small field of view, we have variation. We have a lot of flows, and especially in the later part of the observation, where we have a lot of flows that are loading up mass into the filament or draining it away. And the structure of the filament, the filamentary structure that we see, it's also changed quite a bit. So at the beginning, while we have a very extended width of the filament, and later on we only see a very few strands that are separated, that have been separated and are emitting by themselves. And especially when looking at the variation of the ratio between the H and K line, we can observe how this variation is happening. I then looked at about half an hour intervals during the longer evolution of the filament, and see how the best observables that are identified by the filament changed during this time. At the top, I have average. I have the total distribution of these measurements in blue over the whole data set, and in dark orange over only the filament region I've showed above. So the filament itself has overall a very low K3 intensity, or H3, because these two are similar to each other. The optical depth, the depth of the central reversal is very high compared to a more typical observation, and the ratio between the H and K is very low, meaning that the optical depth is high. But as the filament itself evolves, the variation within the variation of these observables varies quite a bit. So at the beginning, we have it's dominated by very low intensities as we can see from the image too. So at the beginning, we have a very extended region where there is a lot of filamentary material that's contributing to the emission, while later on we have just a few bands or strands from the filament that are still visible within our field of view. As I said, the filament is evolving, so within that same position, we are not seeing exactly the same filamentary structure as it was, either because it has moved itself, or because it is evolving due to numerous flows that are happening at its boundary. So these flows and evolution will, in time, lead to the decay of the filament. So here I'm showing observation of a different filament, because for the one I showed before, I don't have the same field of view for the different days. And for this filament, we have a very similar observation characteristics. So we're observing the same more or less the same field of view over a couple of days. As well, at the beginning, we have a very compact filament. As time goes on, flows are beginning to split up the filament into multiple sections along the polarity inversion line, and later on, but as it rotates towards the disk, towards the limb, we also see the filament ball as in. We are not seeing it straight down, but from a side, and you can see different strands that are highlighted much better in this observation. And as this filament rotates to the limb, we can observe its characteristics, which are not anymore affected by any disk emission, and we can identify, especially in the velocity field, we can identify coherent structures that are have a coherent. We can individualize the flows that have coherent structure within the filament. So we have flows that are coherent material along the filament, but also flows that are carrying material in the plane of the sky along the prominence structure. And combining all this observation if you are interested in different aspects of the filament, we can look both at the emission, but also the detailed structures revealed by the different emission features of the profile. And to sum up this part of the talk, the magnitude resonance lines, because of they form over the whole wide range of chromospheric heights, can probe the so-called height structure within the prominence and filaments, and reveal how these look at different positions. Also, looking at the emission peak separation or the ratio, we can get approximation of the velocity gradients or the average velocity fields that are taking place along the formation around the formation height of the different features of the profile. Doppler measurements on this can reveal shear flows or flows that are loading up mass into the filament or draining it away. While at the limb, we can also see flows within the prominence happening along the filament, the prominence structure. And finally, the ratio between the the two resonance lines will give us information about the density variation within the filament, because the optical thickness is related closely to the escapability of the photons from the plasma, and this is related to how dense the material from each deceleration originates. In the future, I plan to look at the plane of sky motions within the filament, and also explore the relation between the chromospheric emission and the overlaying coronal structures. Any questions so far? If not, I will go to the second part of the talk, where I'll be looking at very much older data for the Skylab era, and trying to probe it for useful lines in the new ultraviolet that we can further use to explore the filamental prominence emission. We are interested in this region because a lot of important contribution to Doppler in the chromosphere are present in this region. For instance, here I'm showing the contribution to opacity of iron-2, which especially where where the lines of iron-2 are very dense, they are important contributors to this opacity, to ultraviolet opacity. But why using Skylab? Because we are interested in the larger near-ultraviolet region, and no more recent observations of this region, of this whole region, exist to date. And Skylab, the data we are using are from the S082B experiment, which was mounted on the Apollo telescope and was used to capture spectra, both in the far ultraviolet and ultraviolet, for a number of phenomena. We are interested in this study only in prominences that are observed in the near-ultraviolet, in the longer wavelength region. And from this, we are only interested in the spectral region to the left of the magnesium 2 resonance lines. It is worth mentioning that because these data are taken on film, and there is no information along the y-axis due to dispersion of the spectra. So for prominence observation, we have when the slit is located along the prominence, we have the information only in one corresponding to one position that is then spread out over the whole film roll. And this proved offered a few challenges. First of all, in order to be able to fully take advantage of the data, we need you to have observations with multiple exposure times taken on the same film roll in order to be able to fully calibrate it. Also, we needed to have different exposure times, and we needed to have decent signal to noise within each exposure in order to be able to use it. So let me go over the analysis, the data reduction process. First, we started from a 2D film data. We then subtracted the background and produced a one-dimensional spectra. We then co-aligned the different exposures in order to match, to at least match the spectral range between them. We then computed the film characteristic curve, which relates the film density to the measured product of the intensity and exposure time. And this is the important step, because we need to have different exposure times on the same film, and but also taken with enough signal to noise in order to be able to distinguish the spectra itself. And this was the most challenging part of the analysis, because getting the correct field density calibration of the film will influence much of the succeeding results. After this was completed, we've merged the different exposure times in order to enhance the dynamic range of the observation. And then we did a wavelength calibration in order to account for stretching or twisting within the film itself. And finally, we divided the obtained intensity by the reflecting curve and obtained the final spectrum we'll be using in the rest of the analysis. A final step that would have been much more useful would be calibrating to absolute intensities, but because no exposure to a known source was taken on the same film roll, this could not be achieved. So all the intensities I'll be presenting further on are only relative intensities and should be considered just within each data set, the relative intensity, and not as taken as absolutes. So after we have obtained the 1D spectra for all of the prominences, we found that we have 6 prominences that have at least one usable film roll that could be used to further in the analysis. But some of them do have multiple film film sets that could be used to check that the calibrations are correct for each one of them, and but also how the prominence will evolve from one day to the next. Here I'm showing a small spectral range close to the resonance lines of iron 2. At the top, I am showing the spectra, the limb spectra from the Optical obtained at 4 arcseconds above the limb, which we are using as reference because this at 4 seconds above the limb, we don't have any other activity, and this will be a very so-called clean spectra that we can compare our intensities to. Then I'm showing the recovered intensities for the different prominences. As you can see, while at the limb spectra, the iron 2 lines are in their optically thin ratio of 1 to 1. When going to the prominence, the ratio is no longer true, and this is again indicative of varying optical thickness within the prominence, from one prominence to the other, and maybe within the prominence itself. As I said, Spectra is characterizing one single point within the 4 prominence, so it's just we are taking this as some average properties of that observed prominence. After we have obtained the spectra, we can try to do a simple calculation to see what the plasma properties within the prominence are based, that will give us the relative intensities as those observed with the different prominences. For this, we have to make a few assumptions. The prominence plasma, because the prominence plasma is only radiated from the solar disk and is optically thick in the various lines. We need to solve for the radiation field in the population through a set of non-relative radiative transfer equations. And given that our observation limitation, the recovered parameters will be, as I said, both properties and average properties within the prominence. We use local escape probability approximation to account for the scattering within the prominence, and we solve for the electron temperature, the electron density, and the color mass of the emitting prominence material. And within our calculation, we take into account the contribution of singly ionized carbon, magnesium, silicon, aluminium, and iron, and we consider a variety of parameters. And after we obtain the average parameters of the plasma, because in this range, wavelength range, you have a lot of iron lines that are sharing a common upper level, we can use this to extract a distribution of lines with respect to optical depth. So here I'm showing goodness of fit hypercube of the different considered plasma properties. As you can see, we have a whole bunch of parameters that would produce a very similar relative intensities to those observed in this case. We then take the best fit and create the simulated emission profile based on this. And we plot it here in the dotted red line. And as you can see, the intensities are not fully recovering the observed ones, which are shown in black. But given that there are a lot of uncertainties in the calibration of the film data, but also in the simplification for the radiative transfer equation, this is a very good fit. And here I'm also showing the recovered properties for this particular prominence. And then, as I said before, we can, because we can have multiple iron 2 lines that are sharing a common upper level, we can compute the distribution of lines with respect to optical depth within the prominence. For instance, for this prominence, we have a very modestly thick prominence. We have a few magnesium is very thick compared to the others, but also have a few iron lines that are also in optically thick conditions. For a more dense prominence, we have much more iron lines that will be optically thick. Therefore, when looking at the prominence material, the different lines will show the different layers within the prominence. So looking from the magnesium towards irons, we'll see different shells within the prominence material, and therefore we can explore the different the flows in depth as we look into the prominence. So to conclude, we have used previously never analyzed data from Skylab, and from this we have identified 6 prominences that have sufficient data that could be used to calibrate and get to pretty good calibration and get pretty good radiative intensities out of them. We then did use a few simple models to take advantage of the large number of lines present in this wavelength region and solve for mean plasma properties within the prominence. And finally, because we have so many lines of iron that are closely related to one another, we can also extract the distribution of lines along the line of sight. And this, because this is important because most of the iron lines and also magnesium too are sensitive to the magnetic field. So this, if magnetic field measurement could be taken in this line, you can also, and on top of the plasma properties, we can also extract the 3D structure of the magnetic field within the structure within the prominence itself. And as I said, because we have a lot of iron lines that are sensitive, they have ratios sensitive either to temperature or to density. We can more closely get the properties of the plasma, the thermal properties of the plasma on top of the magnetic lines. And overall, in the ultraviolet has a wealth of lines that could sample a variety of chromospheric heights, and can prove to be a very good diagnostic for filaments, but not only. And simple analysis can reveal some properties of the plasma, but going to the detailed structures of the profile can reveal flows and substructure within the prominence of the filament. And if, for instance, recent measurements from the class 2 have shown that magnesium the magnesium can offer reliable magnetic measurements of the mid and top chromosphere. Therefore, if we can extend this kind of measurements to more structures to be useful as the future, we may be able to fully look into the 3D structural prominence by looking at magnesium and a number of other iron 2 lines. And thank you. I'll be happy to answer any questions.
Thank you, Daniela, for a very nice talk. So now it's time for questions. You can just unmute and ask your question, or you can raise a hand. Kevin.
Hi, Daniela. Thank you for that talk. I commend you for digging up the old Skylab data and pulling all this useful information out of it. There's a lot of
yeah, it makes one appreciate the modern data much more.
Yeah, but also, film was a unique kind of detector that could give you all these spectral lines at once. So that's great to see. I had a question going back to the iris data, actually.
Yeah.
And you had the Doppler or the velocities that you derived from the position of the absorption line core. And then you had the ratio of the two K2 peaks, right? And they often Yeah, like one of, which one? The next one, maybe. Yeah.
Yeah.
I mean, yeah, here and in the other plots, you see this opposite sign between the line shift, right? That's the shift of the line core, and then the two peaks. Is that just because when the line core is shifted, it ends up lowering? If it's shifted, say, to the blue, it'll lower the blue peak, so then the red peak is. So that peak ratio maybe doesn't really. It's hard to relate directly to a velocity, right?
It just shows more structure than the Doppler shift. That's why I'm showing it.
Right.
And it's also and it's correct what you said, that because we have large scale flows that are shifting the line itself, one of the peaks would be more spread it out compared to the other, and the opposite peak to the shift will be dominated the emission in general.
Right. It won't be as right. It won't be as reduced. Okay. Yeah, no, that split. Yeah, and they were always sort of this opposite sign. That was interesting. So that would explain why. Okay. But yeah, you definitely see the structure more clearly in the ratio maps, even if it's maybe harder to interpret sometimes.
Yeah.
Okay. Thank you.
Thank you for the question.
Other questions? Yuhong.
Oh, yeah, the same map here. Where is the filament spine relative to this Doppler the left? I'm just.
Yeah. So the filament is situated just at the edge of the blue shifted part and over the red part in the Doppler map.
So you're saying it's the spine? Is it between the blue and the spine? Is between the blue and the red?
No, the red is just under the. Let me go back to this one. So the red is happening here along the lower part of the filament, and the red shift is over the filament itself. I should have had a contour or something over it.
So do you think it's consistent with like flow towards the dips or downflows, condensing flows? I mean, is that a good interpretation?
When I've been looking at the AI data, and in the filament, there are flows that are going along the filament at the bottom. So we have flows that are going in the plane of sky along the filament, but that have also a component that stores the observer. But in the filament, we have flows that are going more or less in the opposite direction, that are redshifted, that are going towards the sun. But I will have to look into a little bit more into that. I will only briefly look at that.
This is really interesting. Anyway, thank you.
Yeah, this was a very weird filament. That's why I was showing it.
Phil?
Yeah, thanks, Dana. One of the things that is dynamically significant, of course, is the mass. And to get that, this line ratio analysis for common upper levels, you simply take the column mass and multiply by the projected area. So it gives you an independent measure of material mass within the prominence that is predominantly radiating in these single ions. That is different from what you'd of course get from anything like an electron density. So what this is getting you is, given the thermodynamic state of these things, it's very easy to ionize neutral magnesium and iron in this region of the atmosphere. It's very difficult to ionize iron plus and magnesium plus. You need high electron temperatures on the order of several times 10 to the 4K, and the numbers we're getting are a bit smaller than that. So what this gives you is a real measure of the mass to within factor of 2 to 5 or something like this of the entire prominence. So I just wanted to point that out for those that are interested in those things.
Thank you very much.
Michael? Michael, you unmute.
Hi. I just can't resist to comment that I'm intrigued by this piece of data mining or data archaeology, if you don't mind. And it makes you wonder what other data has never been taken advantage of. I just was reminded by that the spectrostratoscope data, which was a balloon mission by the Kiepenheuer Institute observing solar granulation, was never fully analyzed because the basically image processing techniques weren't developed yet, but everything that was found later in Quark movies presumably is in that data. And while one can sort of harp about that hadn't been done and so on, I think it just for the future points towards that all the DKIST observations and the space-based observation be fully accessible for data mining so that we can really multiply the harvest. Thank you.
Yeah, thank you.
Any other questions? Phil, again.
Yeah, Michael, I'm fully on board with you there. The thing about this set of data, if you look at what's been published with the particular Skylab experiment, again, it had a 2-second wide slit by 60, and it was not in an image plane, so you don't get spatial information, as Dana said. But if you look at what's published, the short wavelength stuff in second order down at between 1100 and 1920 or a bit higher in angstrom, it was very well studied because people didn't get nervous about studying things like lithium-like ions, like beryllium boron-like ions, which dominate the spectra down there. However, when you go to this region, you have this 4p to 4s transition array in the ion group, which gives you hundreds and hundreds of lines, and the atomic data for those things are notoriously difficult to get. So you don't find very accurate, if any, measurements of cross sections or data in something like Chianti. That's because these are neutral and single ions, and a lot of the approximations they use start to break down for very fluffy ions. These are big things that don't bind the electrons very tightly to their cores. And so there's a reason why these haven't been analyzed. And I suspect there's a lot of data all over the sun in this wavelength, particular wavelength channel, which is essentially unexplored. Interestingly, I think probably the Hubble archive has better quality data. Of course, it will have significantly better quality data in terms of calibration. But the sun, especially above the limb, is so rich in its ability to pick out individual ions very clearly, to separate all the blends. And then you have these relative transfer techniques that can tell you things like the total mass, the average electron density, the temperature of the plasma, all things of which people sort of have had to guess from in the past. And now you've actually got techniques to measure them. So I think that the reason this has taken so long to appear in the literature, you know, it's sort of 50 years nearly, is because of the complexity of the ions, the problems in modeling it, and the lack of willingness to really get your hands dirty with such complex spectra. So, you know, I think this is a time where big data can really help, because you know, given some measurements and new measurements in this region, if we ever get those again, then we're in a great position with the magnetic field to probe the three-dimensional magnetic field in these structures. So, you know, I'm really, really intrigued by this stuff, and was surprised indeed that nobody had published these things. But yeah, I don't want to lecture to the congregation here, but you know, I think people are actually quite surprised, and I believe that you know, at the AGU last year, both Holly and Daniela got some interest from people about this stuff. So definitely, this stuff is worth pursuing.
Yeah, you ask yourself why former HAO leadership didn't jump on that, but that's more humorous remark.
But I think the atomic data, it was a stumbling block in those days, and NIST has done a fantastic job of really pulling together all the work of Charlotte Moore and others.
So there is real progress in the atomic data.
Yeah, and you know, for many years, this reminds me of another thing. That is there used to be a order of magnitude discrepancy in the abundance of iron in the sun, as measured from the corona and from the photosphere. And this was finally resolved I think, by a German group in the 70s, who finally got some accurate measurements of photospheric oscillator strengths. And it turned out the coronal abundances were about right in those days. So it's just very intriguing, the history of all this, and shows you the power of spectroscopy once again.
Mm-hmm.
Thank you.
Other questions? I don't see any hand raised. So, okay, if we don't have any more questions, let's thank our speaker again today.
Thank you for listening
Daniela.
and for the questions.